Swayam Prabha. Digital India. Educated India.
So, let us begin again trying to find out a method which will solve the Sommerfeld equation. We have identified its stiffness in the last few lectures. We also identified a method called the compound matrix method, which involves finding out those modes which satisfy a set of boundary conditions. You see, this is a fourth order ODE. You have two boundary conditions at the wall, two in the far stream. So, you can get some kind of analytical structure of the solution in the far stream, because you know there u double prime is 0, this capital U is 1. So, it becomes a constant coefficient ODE, and we found out there are two viscous modes and two inviscid modes, and in each class one mode grows with y, another decays with y. So, if we are solving a problem where disturbance is created inside the shear layer, we would like the disturbance to decay with y, and those are the ones that we have identified as phi 1 and phi 3. And we noted that there is a disparity of scale of variation of these two fundamental solutions. Phi 3 actually grows much more rapidly as you descend inside the shear layer as compared to phi 1. So, this disparity causes the stiffness problem. This was what we concluded, and we came to the conclusion that we will use a method which can do away with these problems. Okay. For example, if I define this fundamental solutions as phi 1 and phi 3, in the last class we talked about that the knowledge of the solution is equivalent to having this solution vector. Say for example, if I talk about phi 1 solution vector, that actually corresponds to, so let us call this as capital phi 1, one of the mode. So, it will have phi 1 and phi 1 double prime, phi 1 triple prime, and of course, phi prime, phi 1 prime, phi 1 double prime, and phi 1 triple prime. So, this is one of the modes, and the other mode is, if I call that as capital phi and write it like this, then we are going to get phi 3, phi 3 prime, right. So, basically what we have done in defining this compound matrix variable, we have taken a 2 by 2 submatrices formed by capital phi 1 and capital phi 3. For example, y 1 consists of these two elements from here and these two elements from here, and that is what you get, phi 1 phi 3 prime minus phi 1 prime phi 3. Suppose I take the first and third from this two vector column vector, I get y 2. If I take the first and fourth from both of them, I get y 3. Then of course, there are other possibilities. I take the second and third, that will give me y 4, second and fourth give me y 5, and third and fourth will give me y 6. These are all possibilities that you can conceive of, right, because it comes from that you have a 4 fundamental solutions, you are picking 2 at a time. So, it is a 4C2 number of variables, right, that is what you are seeing. Now, basically when we go from the phi variables to this y variables, we need to derive those equations, a set of governing equations for this compound matrix variables, and we have indicated how to go ahead. By utilizing the definition of the variable itself, for example, if I differentiate y1 with respect to y, that is y1 prime would be nothing but phi 1 prime phi 3 prime plus phi 1 phi 3 double prime minus phi 1 prime phi 3 prime minus phi 1 double prime phi 3. You can see these two cancels, and this is nothing but the definition of y2 itself. So, one of the equation immediately obtained was y1 prime equal to y2. You can go through the same exercise using the definition of y2 as I have written it down here. You can differentiate it once, and you will get a set of terms that would involve phi 1 phi 3 triple prime minus phi 1 triple prime phi 3. So, that itself is your y 3, and there is the other term that is phi 1 prime phi 3 double prime minus phi 1 double prime phi 3 prime. That is in a sense again y 4. That is what we have obtained. There is a little bit of extra work that you need to do for the other equations. For example, y 3 prime would involve now phi 3 4 prime and phi 1 4 prime, and we know that individually these modes themselves satisfy this equation, and that means what? I can write it in this form, that phi 4 prime should be equal to some coefficient b 1 multiplying phi double prime minus b 2 phi, where b 1 and b 2 are given. You can take a look at that. You can club those terms together, and this is what you get. Phi 4 is b 1 phi double prime minus b 2 phi prime, and this y 3 prime gives you this set of term, right. So, this is one set of term that we have, and this other set of term. This term is easily identifiable as y 5, right. You can see phi 1 prime phi 3 triple prime minus phi 1 triple prime phi 3 prime. Okay. That is what we get. This other set of terms that we have, well, for phi 3 4 prime I just write it in terms of phi 3 and phi 3 double prime. Same thing here, phi 1 4 prime, we write it like this, and we see that this term actually cancels with this term, right. So, what we are ending up with is b 1 times y 2, right. So, that means what? Y 3 prime is equal to b 1 y 2 plus y 5. So, that is easily understood. Now, we can go ahead and keep doing the same thing, and for y 4 prime as we have defined here as phi 1 prime phi 3 double prime minus phi 1 double prime phi 3 prime. So, if I take its derivative, it would not require the orthogonal equation. You can directly differentiate, and that is what you get. That is what is written here, phi 1 prime times phi 3 triple prime and phi 1 double prime phi 3 double prime minus phi 1 double prime phi 3 double prime minus phi 1 triple prime times phi 3 prime, and this two again cancels, you can easily see, and this constitute y 5. So, that we have seen. So, y 4 prime is equal to y 5. Now, if you look at the definition of y 5, it involves the third derivative. So, if you differentiate it, of course, you have to again invoke the orthogonal equation that we have written here, and that is what is done here. So, y 5 prime would be given in terms of this. This first and third term has that fourth derivative that you use in terms of that b 1 and b 2 coefficients, and this one and this one constitutes. So, this is double prime times triple prime combination that gives you y 6. So, this is your y 6, and here you are going to have here, look at this here, b 1 into phi 1 prime phi 3 double prime, and here we have b 1 into phi 3 prime phi 1 double prime. So, what is that? That is your y 4. So, basically then we get a term, this gives us y 6, this set of terms give us b 1 times y 4, and this b 2 term is very easily identifiable, is nothing but equal to y 1. So, I think we have obtained y 5 prime, and then we need to just look at y 6 prime, and y 6 prime we can go through the same exercise, and you can reduce it to b 2 y 2. So, you see this is one of the beautiful aspect of compound matrix method. Our original problem was a boundary value problem. We needed to satisfy 2 conditions at the wall and 2 in the free stream. By the sheer definition of the new variables, we have already satisfied the far field condition. So, now what we could do is, if we can start from the far field, we can march all the way up to the wall, and then we need to satisfy that condition, right. So, basically what we have done is converted a boundary value problem into a kind of an initial value problem, because you have to satisfy one set of condition only, right. So, this is something what we need to do, and however, we make this observation that in doing so we have increased order of the system from 4 to 6, because now we have 6 coupled first order equation. Okay. Now, as I told you that we could start marching from the free stream and we could march up to the wall, but the question is, what do you do as the initial condition for these unknowns? The definitions are here, right. Y 1 to y 6 are known here. We also know how phi 1 and phi 3 varies in the free stream. Phi 1 varies as e to the power minus alpha y, and phi 3 varies as e to the power minus q y. Q has that expression q square is equal to alpha square plus I r e into 1 minus c. So, we can actually get to use this analytical structure of the solution for y equal to infinity and obtain the initial conditions. Let me re-emphasize to you again that we are looking at problems where the disturbances are created inside the shear layer. So, that kind of disturbances give rise to what we call as the wall mode, because the disturbances are predominantly near the wall and they decay away from the wall. So, that is what we said. So, if we now do that, we talk about the wall mode, phi 1 is e to the power minus alpha y, and phi 3 is goes as e to the power minus q y. So, I can use those definitions, then y 1 works out to minus q plus alpha e to the power minus alpha plus q into y. That is easy, right. You can do that. Phi 3 prime will be nothing but q times e to the power minus q y, and this is of course already e to the power minus alpha y. So, those two product will give me this exponential quantity, and you notice that this gives me that exponential quantity, this also gives me the same thing. That is what we have done. We have pulled it out, and this is what we get. Same thing, go ahead and plug those expressions for phi 1 and phi 3 and put them in here. Y 2 will be nothing but q square minus alpha square times the same exponential factor. Y 3 is this, y 4 is this, y 5, y 6 are. Now, take a look at this. What we promised we deliver now. We said that we are going to define a new set of variable which will have identical growth or decay rate, and that is exactly what you are seeing here. This exponential path, they are identical. What matters is basically is this coefficients that remains upfront. And you know, when you are solving a stability problem, what you know is the quality of the solution you cannot exactly quantify. So, that is why I did not put it an equal to sign here. I said y 1 goes like this, y 2 goes like this. So, exact multiplicative constant is not known, because we are solving a eigenvalue problem, we are not solving a receptivity problem. In the receptivity problem, we would have prescribed the quantum of excitation at the wall, and then we could have walked along that line. However, you also notice that I could factor out alpha minus q from every one of this quantity times this, because this is the variation. So, I could normalize everything with respect to y 1, then y 1 would be equal to 1, right. Y 2 will be what? It will be just simply minus of alpha plus q. So, this is it. So, you can go ahead and get this. Now, this is what will constitute your initial condition. You have now a value of y 1 to y 6, you could start far outside the shear layer and start marching downwards. So, it is a fairly easy task. And what has happened? You do not have to anymore worry about the stiffness. You have actually factored out the stiffness by this clever design of the variables. So, what you have is a 6 first order coupled ordinary differential equation with very neatly given initial condition. You can use any method of solution, you can use any method. So, what people have been waiting for a long time, nearly almost 60, 70 years, that was fulfilled by this compound matrix method. In one go, analytically, we have removed the stiffness of the problem by a clever design of the method. This is the reason that we started looking at this, and what we need to do is that we start off with those initial condition in the free stream, and we keep marching to the wall. And what is it that we will have to do at the wall? Recall, at the wall we had the dispersion relation, and the dispersion relation was phi 1 phi 3 prime minus phi 1 prime phi 3, and this was evaluated at the wall, and that has to be equal to 0. So, this is our dispersion relation, because we noted that not all combinations of omega and alpha will ensure this, only a selective ones will do that, and those selective ones are the eigenvalues. So, this is essentially your dispersion relation. And what is this? Look at the definition. This is nothing but y 1. So, what we have to ensure as the dispersion relation is that y 1 at the wall should be equal to 0. That is what we have said. So, satisfaction of the dispersion relation is equivalent to locating alpha omega combination for a given Reynolds number. This is equivalent to satisfying that y 1 should be equal to 0 at the wall. So, that settles all your problem, I suppose, and that is the way. So, what you are going to do is you fix a Reynolds number. Let us say you want to find out what is the instability mode at a given streamwise station. So, the RE that we have defined, what is the RE? RE we have defined here is some velocity scale, which I may like to call it, let us say u infinity, then times delta star by nu. What is delta star? Delta star is the displacement thickness. Okay. So, if I position myself at a streamwise station, I know what is the local displacement thickness, I know Reynolds number. Now, the game starts. We want to, let us say, study the spatial stability problem. So, we also fix omega. that is a real quantity, right. Now, what we are after? We are after a complex value alpha, that is what we will have to do. So, we will choose some value of alpha and then we will solve those 6 set of ODEs, come all the way up to the wall, and if we see y 1 is equal to 0 there, then the guessed alpha was correct eigenvalue. If it is not, then again we will have to conduct the search. Okay. So, if I try to do that, I have an option. There are a few ways of doing it, and I am talking to you about a method which is called a grid search method. So, let us talk about this particular approach, where we want to find out eigenvalues. Now, talking about eigenvalues, you realize that there is not necessarily only one value of alpha that you are looking for. There could be many, right. There could be, for a given R e and omega, you could get many combination values of alpha real and alpha imaginary that satisfies this dispersion relation y 1 at the wall to be equal to 0. So, what we are talking about is finding all possible values of complex alpha that will enable us to obtain all the eigenvalues in one go. So, what you do? This is the problem. Your boundary layer is like this. So, what you do is you are investigating at this station. So, you will assume that locally the flow is parallel, that is why we are talking about u only function of y. So, we will think of as if there is an equivalent constant thickness boundary layer. So, that is your parallel flow approximation, right. Now, what you are doing is you are starting off with these initial conditions, you march up to the wall and you get y 1 at the wall, which is nothing but I will call, let us say, y 1 real plus y 1 imaginary. Ideally, it should be equal to 0. So, what I could do is I could look up the complex alpha plane. Along this, I will plot alpha r, along this, I will plot alpha I. Now, what I want to do is I want to find out the eigenvalue, let us say eigenvalues in this box. Okay. So, what I do is at random I pick up a point here. For this value of alpha, I come from the free stream all the way up to wall and I evaluate this. And if it is not a genuine eigenvalue, this will not be 0. It will only be 0 when your choice is the correct one corresponding to the eigenvalue. Okay. So, what we can do is we can catalog that y 1 real and y 1 imaginary as a function of alpha or alpha I. So, what you could do is in this whole area of interest, you can obtain the value of y 1 real and y 1 imaginary. So, we are not going into the cumbersome business of trying to find out exactly when this is 0. So, then what we do is, of course, we have the values of y 1 real and y 1 imaginary here. We can plot the contours of y 1 real and y 1 imaginary. And which contours are we going to be interested in? We are going to be interested in the 0 contours. So, basically what I would do is perhaps let us say I will get a contour. So, this let us say corresponds to y 1 real equal to 0. Okay, you can't see it, I will write it bigger. So, this is let us say y 1 real equal to 0. I get a contour like this. There will be many such contours, not only one. I mean, it could be filled with all this. Okay. Now, I also can plot the 0 contours for y 1 imaginary. Let us say I get a figure like this. So, this is like your this. Now, you look at this particular point. What is special about that point that I marked with an asterisk? It is nothing but the point where both the real and imaginary parts are simultaneously 0. That is your eigenvalue, right. So, without worrying too much, I could look at into the whole grid and find out where simultaneously the real and imaginary part of y 1 r and y 1 i. I can get a collection of eigenvalues in that box I have chosen. This method is called the grid search method. So, we can do that. Suppose I give you a velocity profile, let us say talk about the simplest possible case, Blasius boundary layer. I will give you u as a function of y, the capital U, and ask you to do this exercise. You can figure it out. Now, you could stop me and quiz me about this part. What is this part? This part corresponds to alpha real equal to negative. But so far, all along we have avoided talking about it. If alpha real becomes negative, then what happens? You see, we have this modes. Let me spend a little time in bringing this aspect, because this was not pretty much obvious well into 90s till we talked about it and we really poked our finger on everyone's eye and say, look, this is the way you have to interpret your results. You know, you will see lots of papers there, people say, oh, there are eigenvalues here, and they do not even want to talk about it. And at the most, one of the paper I saw, they put in some kind of a question mark, like if it is there, it is not known. Okay. So, in that context, we came into the picture, and what we said that, look, our phi 1 goes as e to the power minus alpha 1, phi 2 goes as e to the power plus alpha y, phi 3 goes as e to the power minus q y, and phi 4 goes as e to the power plus q y. Now, so far we have been talking about when the real part of alpha was positive, that made us choose phi 1 for the wall mode. But suppose the real part of alpha is negative, then what I have to do? Nothing. I just choose phi 2 instead of phi 1, right. It's basically that. It's basically that. And what will happen for that disturbance? That disturbance will still decay with height. So, you can still get the wall mode there, right. Now, what happens is the same way I could choose between phi 3 and phi 4 corresponding to what I want to do, right. So, whatever we have done qualitatively, we do not have to do anything different, only just be conscious, aware of the fact that phi 1 and phi 2 have flipped role. What phi 1 used to do earlier, now phi 2 does that, and what phi 2 used to do earlier, phi 1 does that. You do not have to do very much about that. Only thing that you need to do is look at your initial condition. Your initial conditions now need to change, because there we chose we obtain those initial conditions based on the choice of phi 1 and phi 3. But suppose I now talk about the left half plane. This is the famous left half plane, which all of us forgot till mid 90s. So, this left half plane, if I have to look at, I just simply have to rework on the initial condition, and then I can use the same methodology and I can do the same exercise. So, it is very easy now for you to really do this grid search method. All you need to do is two sets of initial conditions. If alpha r is positive, you do what we saw in the transparency, and if alpha r is negative, we will have to make appropriate modification. And then we again go through that same exercise, come from the free stream to the wall and go ahead and do this exercise. So, I can automate this whole process and find all the values of alpha, and this is what actually we communicated in one of the paper, a conference paper. We did not even publish it. We thought it was quite trivial. It should have invoked the curiosity of anyone looking into the picture. And we obtained eigenvalues in the left half plane. Okay. As far as the phase is concerned, if my omega remains the same and alpha has become negative from positive, what happens to the phase? Phase speed is going to flip sign. So, in one case, if the phase was traveling to the right, in the other case it will be traveling to the left. You can do the same exercise with the group velocity, which will not necessarily be concomitant with the phase speed. You will have to work it out. We did work it out, and we found that some of these eigenvalues on the left half plane also travel upstream. What was important or relevant is to find out the importance of those modes, in the sense the imaginary path. The imaginary path decides whether it is stable or unstable, and as luck would have it, they are all very, very stable. So, people were ignorant, but it did not hurt them. So, for zero pressure gradient boundary layer, it became a pedagogic exercise for us to at least establish that, okay, if we have a eigenvalues on the left half plane, we can work them out. It so happens that they are stable. However, I am not guaranteeing, nobody is, that if you change the mean flow, this property will remain same. So, you can have actually upstream propagating modes. Upstream propagation with respect to the group velocity. Group velocity will determine whether it is going downstream or upstream, right. Please do not be convinced by looking at the phase speed. Phase speed is nothing. All of you understand this property of transverse wave, right. What does phase mean? The particle going up and down in the about the mean position, and the relative position of the motion is given by the phase. So, maybe if this point is up, this point is going down. So, this is antiphase to this. And when you look at this beautiful dance of these particles, it appears as if something is going there. That is what we call as the phase speed. But what is important is how is the energy transmitted during this transverse oscillation, and this energy transfer speed is given by that group velocity, right. That is what we figured out, because that is the speed at which the amplitude travel, and amplitude square provides you a measure of energy. So, energy propagation speed is given by the group velocity. So, it is always proper and correct to evaluate your group velocity and decide for yourself whether your disturbance is going upstream or downstream. So, coming back to the thread, I was just telling you that we cannot a priori guarantee that always the upstream propagating waves are going to be damped. It depends on the health of the mean flow. For a 0 pressure gradient boundary layer, that is the Blasius profile, we found that this was damped, but if we keep having flows with other strain rates like the pressure gradient, I can change the pressure gradient, thereby I can change the mean flow profile, and I could get different types of eigenvalue spectrum, right. Collection of all these eigenvalues together are called the eigenvalue spectrum. So, the spectrum will change depending on the extra strain rates like the pressure gradient. What else we could do? We could change the mean flow by say heat transfer, right. We could also do it by mass transfer. So, anything that you can work on, mass, momentum and energy transfer, can change your equilibrium flow, and you study the stability of that equilibrium flow. One can make actually a safe guess that if you have severe adverse pressure gradient, chances are you will have an upstream propagating mode. Isn't that what separation suggests to you? What is separation? The flow goes to like this, and there is a pocket where actually you have a recirculation. Means what? It goes in the opposite direction. There is a bit of work left for someone seriously thinking of doing a dissertation to relate separation with instability and the corresponding upstream propagating modes, right. So, it's a very viable problem that one could look at. Okay, so, I think we have talked about the eigenvalues and their meaning whatsoever. What is left off? We still have to talk about the eigenfunction. How would this eigenfunctions look like? Now, what is eigenfunction? Well, eigenfunction is nothing but that amplitude of the V disturbance component velocity, right, that we wrote in terms of a combination of phi 1 and phi 3. So, if for a problem I know what this A 1 and A 3 is, and if I can contrive to get phi 1 and phi 3, I can talk about what phi is. That is my eigenfunction. Unfortunately, in adopting this compound matrix method, we did not find out phi 1 and phi 3. We found out those y 1 to y 6. So, what do we do? Well, it is not very difficult for one to imagine what to do is that having defined phi like this, I could obtain its derivatives like phi prime, phi double prime and phi triple prime. They all constitute the solution, because your eigenfunction is governed by the orthomorphic equation. So, any derivative less than the highest derivative constitute a solution. So, these are 4 possible candidate solution components. What is unknown here? A 1 and A 3. So, I could eliminate A 1 and A 3, solve for it and plug it in there, right. And then what happens? I get an equation for phi in terms of those phi 1 and phi 3 and their derivatives, right. I would not do it. Instead, I will ask you to do it and submit it to me. This would be your second assignment, to evaluate this 4 possible combinations of solutions. Okay, so, basically then there are many ways of eliminating A 1 and A 3, 4 are listed here. Is it all inclusive? Well, I'll let you ponder about it and decide for yourself. This has all possibilities, or there is something that is left behind. Well, I will give you a hint. This is all there is to it. So, you prove it that it cannot be more than this. right. You can do that. What you notice is those compound matrix variables that we have evaluated on our way going from free stream to the wall, they appear as coefficients here. So, what we have this coefficients also stored as a function of y 1 to y 6 as a function of y. So, there are 4 possibilities, right. I do not know if I have talked about it here or not, but I will ask you a question. Yeah, I think we have just talked about it in words. Now, I will explain to you what it means, that having obtained y 1 to y 6, in principle we can obtain phi by solving any one of those 4 equations. Of course, whenever you have too many options, you are in a quandary to find out which one would be preferred, and preference would be in terms of accuracy, also in terms of consistency, right. Why do you worry about consistency? I want you to think about it. I will talk about it in the following way. If you look at those 4 equations, the coefficients are y 1 to y 6. So, if I am looking at those 4 equations in the free stream, I have an estimate for y 1 to y 6. That is what we have done it in the beginning of this lecture today. We got those initial conditions. So, we can plug those things. So, at least as far as those 4 equations are concerned, we can look at the property of the solution of those 4 equations, because they turn out to be a constant coefficient ordinary differential equation. And if it does, then we can obtain the characteristic exponent of the solutions, right. I think we have a bit of it here. Say, look at the third equation. Let me just go back and write it down somewhere, so that we can look at it and discuss about it. The third equation, as given here, is y 2 phi triple prime minus y 3 phi double prime plus y 6 phi prime equal to 0. Now, if I look at those initial conditions earlier, what did we have? What did we have? Let us go back and check them out. There it is. So, what happens is, this is your minus of alpha plus q, and y 3 is alpha square plus alpha q plus q square, and y 6 is alpha square q square. So, what do we say about this equation? The coefficients are identified for you. So, these are those 3 coefficients, and you will have 3 roots, but wait a minute, what did we start doing with the compound matrix method? We only talked about 2 modes, the ones for the wall modes which decay with y, and this is a third order equation. So, it will have 3 modes. But the good news is, you see, this starts off with the first derivative. So, one of the mode is neutral mode, e to the power 0, right. So, what happens is we can go there and work out all these 3 modes. Okay. Well, one thing is for sure, you know that you originally started with the exponent of minus alpha and minus q. So, those 2 are there or should be there. So, what you can do is you can deflate this equation, remove those factors out, phi plus alpha and phi plus q, and then you will see that the third root is like this. What is this third root? Looks like something which we did not want to have. It has come about, isn't it? Because we want to have only those modes which decay with y, and here is a mode which actually grows with y if alpha really is positive. And we, well, it may look somewhat cumbersome, but you can reason it out that this mod q is much greater than mod alpha. So, we can eliminate this in comparison to q, and then this q cancels, and then this factor actually goes like this. So, what happens is, by being little careless, what we wanted to avoid, we have invited it back through the back door. So, we get the third mode which we did not want. It does not belong there, it grows with y. So, you see, this was such a simple thing, but it took some time to realize that it should be so. So, what happens is this equation, this third equation that we have identified here, that 15c, is not something I would like to dabble with, because it has a spurious mode. You can go through this exercise and do it for all the 4 equations, and what you would find that corresponding to the first equation, which is a second order ODE, you have 2 modes with the correct exponent, minus alpha and minus q, that is what we want. So, this looks like a consistent equation. C was not a consistent equation, right. You look at the second equation, which is also a third order equation, and it has 3 roots, and those 3 roots, 2 of them are the ones which we are looking for, the third one is alpha plus q, and this one we talked about just now, C, and the D is this alpha minus q and 0. That is a third order equation. Good for us that one of the mode actually corresponds to exponent equal to 0. That means that will not vary with y, that would be a sort of some constant. So, out of these 4 combinations, you could choose which are the ones that you could choose, the first one and the last one. The first and the last one are the ones that we can accept it, while the second and the third one have spurious mode. This is really a violently growing mode. You should never touch B, because q is large and you have a mode which is alpha plus q. So, this will be this will involve the viscous unstable mode, and this one will be inviscid unstable mode, while these 2 are acceptable. Now, these 2 are acceptable, but which one to choose? Which one to choose? Let us look at those equations and decide for ourselves which one to choose. You see, what have we done so far? We have obtained this y 1 to y 6 by marching from free stream to the wall. Now, what we want to do is we want to do the other way around. We will start, because we have the conditions given at the wall for phi, is not it? What is the condition given at the wall? Phi and phi prime is 0. Now, I have to choose between A and D. If I look at equation A, at the wall what it is? This will be 0, phi is 0, phi prime is 0. What about phi double prime? Will be 0. How? We are talking about eigenfunctions. So, if it is eigenfunction, what does it do? It satisfies the dispersion relation. And what is the dispersion relation? Y 1 at the wall equal to 0. So, what we have here, phi double prime becomes of the form 0 by 0, is not it? I can post this 2 term on this side and divide by y 1. So, I will have a 0 by 0 form. So, it becomes kind of an indeterminate quantity. So, you got to realize that. So, it is not very trivial to handle this. Now, whereas, if you look at the fourth equation, you do not have such a problem, because this part will go to 0 and you will be solving this equation, and it should be okay. So, in a sense, what I am suggesting to you, that if you are solving eigenvalue problem, then it would be advisable to use the fourth equation rather than any other one. 2 are unstable, 1 is difficult to handle at the wall. Well, people have made all kinds of observations saying that okay, if it is indeterminate at the wall, so what, you do not do that. You actually solve the Orson field equation itself by one step or few steps, and then you start off using the first equation. It is not elegant. It is not elegant, because the problem of stiffness, growth of parasitic error do remain. Okay, so, we have come to a stage where we are in business. It took us about 60-70 years of hard work to come to a stage where we could get some results. It is not that people at earlier times did not have these results, they did, but accuracy of those results are in question. They have to do lots of extra work. You can do all kinds of procedure of Gram-Schmidt orthonormalization, etc. To do all that, that meant horrendous amount of work, but what you are looking here is very elegant, simple solution. And this simplicity has come about because you spend more time on the drawing board, less time in the computer. You have the other alternative. You do not want to work with compound matrix method, you will have to do lots of jugglery with computed solutions. Okay. So, what did we start looking at? We started looking at spatial instability problem. So, for a given Reynolds number, what we did? We fixed a frequency. Let us call that frequency in hertz as f. If I give the frequency in hertz as f, what will be the dimensional circular frequency? In terms of radian per second, that will be 2 pi f, right. 2 pi f will be so many radians. So, f is what? Cycles per second, omega is radians per second, and if I want to non-dimensionalize that omega, what I should be doing? Radian has no dimension, right. Second is the only quantity. So, if I want to non-dimensionalize omega, I should multiply it by a time scale. And what is the time scale? A time scale should be the length scale by the velocity scale. So, omega naught is basically the non-dimensional circular frequency, right. This I could write it in this particular form. What I have done here, I have written there 2 pi f nu by u e square. So, that I have a factor here u e delta star by nu. U e delta star by nu is Reynolds number, a non-dimensional quantity. So, this quantity also in parenthesis will be a non-dimensional frequency, which I call as capital F. So, what I have here omega naught is equal to f into R e. So, if I investigate the R e omega naught plane, a constant frequency lines would be where f is equal to omega naught by R e. So, these lines originating from there, the origin of this are going to be a constant frequency. So, I think we will stop here. We have lots of things to talk about. This looks like a very simple diagram, but we can write a lot to explain the properties. All that we are seeing that frequency increasing, we are going to go this way. And what is important for one to understand, that there is a critical value below which whatever you do, any frequency you take, they are all going to be stable, because the solid line indicates here the neutral stability. Inside you have unstable region, outside you have stable region. I think I will stop here, it needs a little more careful observation.